Okay, so let's look on self-adjoint matrices and let's try to prove that their eigenvalues are always real. And when I say self-adjoint matrix, I mean a symmetric matrix in the real space and Hermitian matrix in the complex space. And when I say self-adjoint, it means that a matrix equals its self-complex conjugate, or let's say transpose self-conjugate self-complement transpose of the complex conjugate. Okay, think about real symmetric matrix in the real case and Hermitian matrix on the complex case. Let's start to show why their eigenvalues are always real, and we start with a symmetric matrix, namely we are on the real space, but the proof is totally similar for a Hermitian matrix. We will also see this shortly. So let's start with a symmetric matrix. Now, we will take a eigenvalue, which we'll call lambda. We will take it from the complex space, namely scalar from the complex space, to show that even the scalar from the complex space, it will be real in the end. Okay, so we'll take a eigenvalue this and an eigenvector. Remember that eigenvector is always non-zero. We will call the eigenvector x, and we will show, and we know per definition for eigenvalue in eigenvector of a matrix that ax equal lambda x. Okay, so remember the inner product, we can write it as inner product of two vectors, and we will look on the inner product of ax with x. In one case, we can replace ax with lambda x because this is definition for eigenvector that we an eigenvalue that we just saw, and we can say that it equals lambda inner product x and x. This is because you can take the scalar out. Now we can also say that ax x inner product, because this is a self-adjoint matrix, the real symmetric but also the Hermitian, we can say that it equals inner product of x with ax, right? Now, because of this, you can say, again, because of the definition for eigenvalue and eigenvector, that ax equal lambda x, so we can say that it equals inner product of x with lambda x. You can take the lambda now out because it's a scalar, but because we are taking the inner product in a complex space, when we take a scalar from the right side of the inner product, we need to take it as a complex conjugate, let's call it. So there is a little bit of a line above the lambda, you see it. But in both cases, we started with a inner product of ax with x. So the two results equals each other. It means that lambda inner product x and x equals complex conjugate of lambda x and x inner product. Remember that we are talking about eigenvector, and a norm is defined by the vector with itself in your inner product. Now the norm is always greater or equal 0, and it equals 0 only when the vector is 0. Now we're talking about eigenvectors for x, and the norm equals 0 only for the 0 vector. But by definition, eigenvectors are not 0. So inner product of x, which is the norm squared of x, will be always greater than 0 because we're talking about eigenvectors. So in order to this to be true, we must have that lambda equals complex conjugate value. Okay, this is exactly the same for Hermitian. You can see it very quickly, but the proof is exactly the same. So Hermitian, we also get lambda equals complex conjugate of lambda, and by definition, for a complex number, if it equals its complex conjugate, by definition, it's a real value. So let it be symmetrics or Hermitian self-adjoint matrices. We use this self-adjoint in the case that ax x inner product equals inner product of x and ax. So by definition, we got that the eigenvalue is real. This is what we wanted to show, that in real matrices and in Hermitian matrices, namely the complex space for a self-adjoint matrix, we get that the eigenvalues are always real values. Okay, so this was the point, and thank you very much. If there are any mistakes or corrections, please tell me. And that's it for now. That's it.